Hello everyone, myself K. Nitya from the Department of Artificial Intelligence and Machine Learning, St. Joseph College of Engineering. In this video, I am going to explain the special cases of rotations involved in AVL trees. So rotations in the sense in AVL trees, the balance factor is calculated for each and every node. If the value of the balance factor of that particular node falls under the category of 0, -1 or +1 means then the resultant AVL tree is said to be a balanced or height balanced binary search tree. If the balance factor of any of the node present in that AVL tree is apart from the values of 0, -1 or +1 means then that particular tree is considered to be imbalanced tree. So if in some cases of imbalance occurred means we need to perform some rotations. Some the rotations involved in AVL trees are single rotations and double rotations. In single rotation, left and right rotations are performed individually for a single time only. Whereas in double rotation, we can perform left and right rotations in consequent sequences, and we can achieve the imbalancement into the balanced one. So for this, we need to do two types of rotations. One is left and right rotation, and also the second one is right and left rotation. So that in this type of rotations, we are performing both left and right rotations. That's why it is categorized under the topic doubly rotations or double rotations. Okay, so here I'm going to explain in this video if any rotation is happening in case of some special cases. Okay, so I'm going to explain this for all the four rotations. That means for two rotations for single rotation and two rotations for two types for the double rotations. The first one I'm going to explain is LL rotation with special cases. For the LL rotation, we are going to perform only the left rotation for in the AVL trees. So here the structure of the AVL tree is different in the special cases apart from the normal cases. Here I am going to explain the syntax or one syntactical structure for this type of rotation. So here consider the structure. The A is the root node and there is a node called B which is the left child for A, and this A is having one right child called AR. R means right child of A, and for B we are having one node, that means the left node as C and some other node as the right child for B. So here now calculate the balance factor for this node. So here the balance factor for these nodes are, this is 0 here, this is 0, and now this why I am taking this balance factor as 0 means here C and the right child of B is the these two nodes are the leaf nodes. If we are encountering a leaf node means then there is no left or right child for these two nodes. That's why the balance factor is 0 here. And coming to this point, here the right subtree and the left subtree's height is 1. So here 1 minus 1, that is the height of the left subtree minus height of the right subtree, means we will get 0 here. And also here there is no children for this node, then the balance factor is 0, as we can consider this as the leaf node. And now for this node, here the height of the left subtree is 2 and the height of the right subtree is 1, then 2 minus 1 is 1. So till now there is no any imbalance in these nodes. While I am going to insert one more node in this point of C, means here in this point if I am inserting another node means what will happen, then the balance, this particular node becomes the leaf node, and the binary balance factor for this leaf node is 0 here. And what about this one? This is, if I am keeping this node as the left subtree means then the resultant will be here 1, and here for this node the height of this left subtree is 1 and 1, that is 2. So here this becomes 2 minus 1, so this is 1. And for this node the height of the left subtree is 1 2 3, so 3 minus 1 means 2. Now here imbalance occurred, so that means I am inserting the value or a node to the left or right child of this position, and this is the left child of the left subtree. So here the imbalance occurred is LL imbalance. So if imbalance occurred means I need to perform rotation. So what will happen? The rotation will be LL rotation. So LL rotation in the sense I need to perform only left rotation. So left rotation in the sense in this point only we got the imbalance. That means keeping this point as the pivot point and dragging everything towards the right side. Like this means what will happen? A will come to this point and AR will come move to the next level, and B will come to this point along with all these child nodes. Okay, so now B becomes the root node for this point, and A will come as the right subtree along with its sub child AR. Okay, and now what will happen? This B comes to this point, then it will be followed by C also along with its children, and now C will be followed with B, and also if I am inserting one more node, either it is left child means what will happen? If that means this is the C, left child of C means what will happen? It will come to the left of C. Okay, and here B is the root node and A is the right child of B, and AR is the right child of A. Then I have included the nodes A, AR, B, C, and the left of C. And what about this right child of BR? So this is the special case we are going to learn here. Okay, so here the this node is the right child of B, so it must come towards the right of this resultant tree structure. That means, so this is the center point and this is the left subtree and this is the right subtree, and what will happen? This particular node is the right child of B. So it must come to the right side of this resultant tree only. So what we can do is I can attach this right sub child of this B to A. That means it will come immediately to the next level of B. That's why I am attaching here, not here. Okay. So here this is the right child of B. Even though it is the left child for EA, but this B is still in the right side of B only. That's why we are simply shifting this right child of B towards A here. Okay, so this is the special case we have learned in LL rotation. So I am going to explain this particular rotation with one simple example. So I am writing this basic structure here. So that means LL rotation in the sense, so A and B is the left child of A and AR is the right child of A, and here C is the left child of B and BR is the right child of B, and I can insert either CL to A C, or that means left of C to left or CR to the right of C. If I am doing this means I will get imbalance in this particular tree, then I'm going to perform the left rotation, that because this two insertions are happening to the left child of the left subtree. That's why it is called LL imbalance, and I'm going to perform LL rotation for this. So then what will happen? At this point, I am dragging everything towards this point means B will come here and A will be shifted towards the right hand side and it will be followed with right child of A and C will be here. C and either this CL or CR will be attached to this node C and what about this BR? It is simply attached towards the left child of R. Okay, so in this method only we are going to maintain the balanced structure of the binary search tree that is called AVL trees. Okay, so for this I am going to insert some values now. So consider the values 50, 30, 70, 20, 40 and 10. So these are the given values we need to these are the given values we need to insert in a AVL tree. I'm going to construct the AVL tree using these values. Okay, so let's check whether we are going to encounter any imbalanced format while inserting or constructing the nodes into the AVL trees. Okay, so now first step is insert 50. So this is the first step. While inserting 50, what will happen? 50 is the root node here. So this 50 is the root node as well as it is the leaf node. So the balance factor for this node is 0. And I have inserted 50. Now I am going to insert 30 now. So now the second step is inserting 30. So that means compare this 30 with 50. What will happen? 30 is smaller than 50. So the resultant will be 50 and 30 is inserted towards the left side as the rule of the binary search tree is the child's value must be less than the parent node and the right value of the child must be greater than the parent node. So that's why we are inserting 30 here. So the balance factor for 30 is 0 as it is the leaf node and for 50 the left subtree's height is 1. So 1 minus the right, there is no right child, so it is 0. So 1 minus 1 is 1 here. Till now there is no imbalance occurred in the balance factor. So we have successfully inserted 30 and now insert 70 here. So that means if I am going to insert 70 means what will happen? I need to compare this value with the root node. So now 70 is greater than 50. So that means I can insert this 50 in the right hand side of the root node. So the resultant will be 50, 30 and here 70. So that means the both the 30 and the 70 nodes are leaf nodes. Then the balance factor is 0 here and here the height of both the subtrees are 1. So 1 minus 1 is equal to 0 here. So till now there is no imbalance occurred. So no need to worry about the balance factors. So now we have inserted 70. Now moving towards the next values, insert 20. What will happen if I am inserting 20 means compare 20 with 50. So 20 is lesser than 50. So I am moving towards the child node. Here 20 is also lesser than 30. So I need to insert 20 to the left of this 30. So the resultant will be 50, 30 and 20 here. And here also we are having one value called 70. So this is the balance factor of this 70 is 0. The balance factor of 20 as it is leaf node is it is 0. And for 30 it is 1 minus, there is no right subtree. So 1 minus 0 is equal to 1. And the left subtree's height is 2 here. So 2 minus here 1, that means 1. So no issues in the balance factor. Now we have successfully inserted 20. And what about 40 here? I am going to insert 40. So now if I am inserting 40 means I need to compare this 40 with the root node. So 40 is less than 50. So immediately come to the child of this root node. So now compare this 30 and 40. 40 is greater than 30. So it must come at the right side of this 30. So the resultant will be 50, 30, and here 20. We need to insert 40 here along with the right child of 50 as 70. So here the 20, 40 and 70 are leaf nodes. So the balance factor is 0, and here the height of both the left and right subtrees are 1. So 1 minus 1 is equal to 0. Now for this left subtree, the height is 1, 2. That is the levels are 2. So this is 2 minus, here it is 1. So 2 minus 1 is 1. So after inserting 40, there is no imbalance occurred in this point. So we move on towards 10, inserting 10. So now for the sixth step, I am going to insert 10. The node 10. Okay. So now 50 is there. This is 30. Here it is 20. Here 40 and 70. So this is the previous tree structure. Now I am going to insert 10. So compare this 10 with 50. 10 is lesser than 50. So I am moving towards the left child of 50. Again compare this 30 with 10. So 10 is less than 30. So moving towards the left child of 30, it is 20. Now compare 20 and 10. 10 is less than 20. So I am inserting 10 at this point. Okay. So now calculate the balance factors for all the nodes. So the for 10, 40 and 70, all the three nodes are leaf nodes. So the balance factor is 0 here. And for this 20, it is 1 minus, there is no right subtree. So 1 minus 0 is equal to 1. And here it is 2 minus here 1. So this is 1. And 1, 2, 3. This level is 3 minus this is 1. So 2. Now in this point only we have encountered the imbalance structure. Okay, so that means we need to perform some type of rotation. I need to find out what type of rotation is going to um, what type of rotation is needed to be performed here. Okay, so for this I need to find out what type of imbalance occurred. So that means while inserting 10 only, I got this imbalance. So 10 is inserted to the left child of left subtree. That's why we are calling this as LL imbalance. If LL imbalance occurred means we need to perform LL rotation. So for this LL rotation, simply keep this point as a pivot point and simply drag everything towards the right hand side of the tree. Okay, so then 50 will come towards this point and 70 will come to the next level below it. Okay, and 30 will be the root node for this, along with 20 to this previous level and 10 to this previous level. So I'm going to do this like this. So here the 30 is the root node and 50 is the right child, and 70 is the right child of 50, and this 20 will be the left child of 30. Okay, so this is 20 and here this 10 will come to this point, and I have inserted 10, 20, 30, 50 and 70. Then what about this 40? Here comes this structure, this BR structure. Okay, so that means this is the right child of B. So that 40 is the right child of 30. So 40 must be present in the right side of this 30 only. That means I can attach this 40 to the left of 50. Still 40 resides on the right side of 30. So now calculate the balance factor for all these nodes. So 10, 40 and 70 all are leaf nodes. So we can put the balance factor as 0 here, and for 20 there is no right subtree. So here there is only one level in the left subtree, so it is 1 minus 0, it is 1 here, and for this here 1 minus 1 is equal to 0, and for this the left subtree's height is 2 and right subtree's height is also 2. So 2 minus 2 is equal to 0. So that means we have encountered one imbalanced structure in this point, and we have found out that we have determined the imbalance, how this imbalance occurred, and we have performed the rotation for this imbalance, and we have achieved the balanced structured binary search tree. So this is the type of rotation, LL rotation, with the special case of attaching some values to the previous nodes. Okay, so here we have performed only one single node, single rotation called left rotation. That's why it is categorized under single rotation, LL rotation. Next, I'm going to insert. I'm going to explain the second type of single rotation called RR rotation. So for RR rotation, we are going to perform only right rotation for a single time only, but with some special values attached to other nodes, we are going to give some more care to that particular node. Okay, so for this, I'm going to draw the structure. Here, A is the root node, and AL is the left node of this A, and also B is the right node of A. Now I'm having one more node called BL, which is the left of B, and C as the right node for, I mean, right child for B. Now I'm going to insert either left child of C or right child of C in this point. Okay, so what will happen? Here for this structure, the balanced factor is this is 0, this is 0, and 0 minus 0 is 0, and here this is 0, here 1 minus 1 2, this is minus 1. There is no imbalance at all. But if I am going to insert anything here, means what will happen, this will become 0, and this one is, if I am going to insert only one left child, means this means this is 1 here, and this is 1 minus 1 2, this is minus 1, and here this is 0 1 minus 1 2 3. So what will happen, minus 2, here imbalance occurred. So why imbalance occurs, because I have inserted one node at least at this point, so which means this is the left subtree of right sub subtree's right child. So RR imbalance occurred. I need to perform the RR rotation for this point. So at this point, I'm going to do one single right shift only, right rotation only. So keeping this as the pivot point and moving towards this, that means dragging everything towards the right hand side, means what will happen, B will become the root node here. So root node, and A will be the left of B, followed by the left of A, and C will come to this point. So C will be here, and now if I am inserting CL, means CL will be here. And what about this BL? That means this is what we are going to taken in account in this case. Okay, so BL means this is the left child of B. That means it must reside to the left of B only. That means we are going to insert this BL to the left subtree of this B. So this this BL node is the child of B, left child of B. So I am immediately placing this node to the next level of B itself. But next level of B is having A as its child. So I am going to insert the BL towards right of A, so that BL always remains in the left side of the B node. Okay, so for this I'm going to explain, I'm going to take one simple example to explain this concept. So consider one tree like this. Here the root node is 20, and 10 is the left child of 20, and 40 is the right child of 20, and now 30 is the left child of 40, and 50 is the right child of 40. Okay, now I am going to insert one node called 60. For this, given AVL tree. So we need to check whether this is a balanced one or not. For this, I'm going to find the balance factor for this. Now, the 10, 30 and 50 nodes are leaf nodes. So the balance factor is 0 here. And what about 40? 1 minus 1 is 0. Here, 1 minus 2. 1 minus 2 is minus 1. So this given tree is a height balanced AVL tree. Now I'm going to insert 60 into this tree. Okay, so if I am going to insert this tree, say 60 into this tree means I need to check whether still the height is maintained as a balanced one or not. Okay, so for this, while I'm going to insert 60 means it is compared with this root node. The root node's value is 20, so 60 is greater than 20 means it will come towards this point. That means 60 must be present in the right hand side of 20. So here also we are having one node called 40. So compare 40 and 60. Obviously 60 is greater than 40, so move towards the right hand side. Now check whether this 60 is greater than 50 or not. Yes, of course it is greater than 50. So insert 60 to the value of 50, node 50. Okay, so now we need to calculate the balance factor for this tree. So the 60 is the leaf node, so the balance factor is 0 here, and for this there is no left subtree, so this is 0 minus the height of this tree is 1, and this is minus 1, and here we are having one tree, one left subtree, and there is two levels, so 1 minus 2 is minus 2, and here it is 1 minus 1, 2, 3 levels are there, so 1 minus 3 is equal to minus 2. Okay, so what will have what happened here? Here for these two, one, sorry, this is 1 minus 1 is minus 1. And now at this point only we have encountered the imbalance. So what type of imbalance occurred? It is while inserting that node 60 to the right child. This is the right child of the left subtree. So imbalance occurred is RR imbalance. So I need to do RR rotation. I need to perform RR rotation to correct the imbalance. So what I'm going to do, keep this thing as a pivot point and drag everything towards the right hand side or left hand side. What we will do for RR rotation, we are going to drag everything towards the left hand side like this. So 40 will come to this point and 20 will come to this point and 10 will go to the next level, next level in the right hand side, and 50 will come to this point and 60 will come to this point. And now what about this 30? We will see now. So 40 will be the root node for this thing, and 20 will come to this point along with 10 here, and 40 is followed by 50 in its right hand side, and 60 is following 50. And now I have inserted 10, 20, 40, 50 and 60. Now what about 30? So this 30 is the right child of 40. So it sorry, left child of 40. So it must reside in the left subtree of 40 only. That's why I am simply attaching this 30 towards 20, because for left child 20 is there for 40. So I cannot put this 30 here, but I can put this 30 here as 30 is greater than 20. So now calculate the balance factor for all the nodes. So these three are leaf nodes. So the balance factor is 0, and here 1 minus 1 is 0, and here there is no left subtree. So 0 minus here 1, this is minus 1, and this is 1 2 minus this is 1 2. So this balance factor is 0. Okay, so we have corrected the imbalance and we have achieved the balanced structured AVL trees. Okay, so here also we have performed only the right rotation. Okay, so that's why this right RR rotation comes under the category single rotations with special cases. The third one I'm going to explain is LR rotation. So for this, the schematic diagram is like this. A is the root node and B is the left child, and now BL is the left child of B, and here C is the right child of B, and AR is the right child of A. Now I can insert CL or CR to this C. Okay, so if I am inserting this means I will encounter the imbalance in the balance factor. That means here if I am inserting this means this is 0, this is 1, here 0, 1 minus 1 2. So 1 minus 2 is, this is minus 1, here 0, here 1 2 3, 3 minus here 1 is minus plus 2. So imbalance occurred at this point. So in this point, what type of imbalance occurred means, while if I am inserting left child of this C means it is inserted to the right child of the left subtree. So the imbalance occurred is L or imbalance. Imbalance occurred is L or imbalance. So I need to perform L or rotation. So for L or rotation, I need to perform in the first step, I need to perform R rotation, right rotation. So right rotation in the sense, I'm going to taking care of these three nodes only, because these three nodes are the main special case here, because inserting the new node at this point only causing the imbalance to this point. That's why I'm taking these three nodes as for consideration. Okay, so here I'm going to perform the right rotation. So right rotation in the sense, I'm going to take this B as the pivot point here. So if I am taking this point as pivot point means I'm going to drag everything towards this side. So if I'm dragging everything towards this side means here A and AR remains same untouched. So A will be here, AR will be here, and this C will come to this point by dragging this B here with BL here. And now this CL will come towards this point. Okay, how? This will come towards that point in the sense, this CL is the left subtree. Okay, so still it is remaining in this point only. So this will come to this point. Okay, and now we have performed our rotation. Now I am going to do the next left rotation. So that means here I am going to perform the second step of doing the left rotation. Left rotation in the sense, I'm going to keep this point as the pivot point and dragging everything towards this point. Okay, right hand side. Okay, so what will happen? C will come to this point, A will come to this point, and A will move towards A, R will move towards the next level, and B will move upwards to its previous level along with BL. Okay, so what will happen? C will come to this point. So C will be in the root node with A and AR as its right subtree, and B and BL as its left subtree. Then what will happen to this CL? CL means this CL is left child of C. So it must remain in the, consider this thing, consider from this first structure. So CL is the left child of C. So it must remain in the left side of C only. So I can attach this CL to the left child. So left child means the immediate left child is B. So I cannot attach here, but there is no left child there. There is no space for attaching left child, but we have one more space in the right child. So I am inserting CL so that the left side child of C is always remaining in the left subtree only. Okay, so now calculate the balance factor for all the leaf nodes. The balance factor for the leaf nodes is 0, 0, and here 0, and this one is 0, 1 minus 1 is 0 here, and here there is no left child, so it is 0 minus the height is 1 here, this is minus 1, and now for this left child the height is 2, and here also 2, so 2 minus 2 is 0. So in this way, we have achieved the balance in a perfect order. Okay, so I am going to explain this with an example. So consider this tree as a structure. 50, 30, 20, 40. So consider this three. So in this tree, if I am going to insert 35, if I'm going to insert 35 as a node for this 40, means what will happen? It will come in the left side only. So calculate the balance factor here. So before inserting the balance factor for this tree is these two nodes are leaf nodes. So it is 0 and 0 here, and here it is 1 minus 1 is 0, and also here 2 minus 1, this is 1. And if I am inserting a value called 35 here, what will happen? The balance factor here is 0, and here it is 1 minus 0 is 1, and here 0 1 minus 1 2, that means it is minus 2, and for this 1 2 3, 3 minus 1 is 2. So at this point imbalance occurred. So imbalance, what type of imbalance occurred? Means while inserting the node 35 to the right of left subtree, only imbalance occurred. So I can perform left right, that means LR rotation to this to overcome the imbalance occurred here. Okay, so that means we are going to consider this point only. So for this point, first I need to do the, in the first step I am going to do the right rotation. So right rotation in the sense I am simply dragging everything towards the right hand side, left hand side like this. So what will happen? 50 will remain there, and 40 will come to this point, and 30 and 20 will be in this left subtree like this, and this 35 is the left subtree of 40. Okay, so what will happen? It will come to the left side. Okay, so in this left side means we cannot put this 35 here, so I am keeping this like this. Okay, so now I have performed right rotation. In the next thing I am going to perform the left rotation. This is the second step. I have completed right rotation. So now keeping this thing as a pivot element, pivot point, and dragging everything towards the right hand side means this 40 will come to this point, and 50 will come to the next level along with 30 here and 20 here. So what will happen? It will be 40 here, 50 here, and 30 will go to this previous part. Now 20 will be here, and what about this 35? So this 35 is the right, from this question, from the previous first starting, 35 is the left of 40. So it should reside in the left of 40 only. So I can place this here as the 35th value. Okay, now consider this tree. Find the balance factor here. So the balance factor for the leaf nodes are 0 here, and for this node it is 1 minus 1 is 0, and here it is 2, 2 minus 1 is 1. So now we have removed the imbalance occurred in this point, and we have achieved the height balanced binary search tree using double rotations called left and right rotations. So this is the third case in the AVL trees rotations, with some special cases like this insertion at some other intermediate nodes. Okay. So the schematic diagram for the oral rotation will look like this. So here A is the root node and AL is the left node for A and B is the right node for A, and here C is the left for B and BR is the right for B. Now if I am inserting CL or CR to this particular node means it will lead to some imbalance. Then what type of imbalance occurred? I need to find whether if I am inserting this left child of C means it is inserted to the left child of right subtree. So RL imbalance is occurred, so I need to perform RL rotation. Okay. So for RL rotation, consider these three nodes only. Okay. Because then here only we got the imbalance. Okay. So here for RL rotation, we need to perform the first left rotation. In this first step, I need to do the left rotation. So in this case, I'm going to take this point as the pivot point and simply dragging everything toward the right hand side from the left. So remind this A and AL remains untouched. So here it is A and here this will be AL and this C will come to this point. So here C and B will come to this point and BR will be there. And here for this C, if I am inserting CL means it will come to this point. But still one more rotation is needed because I have completed only L. So if I am doing this as the second step, I have completed L, but now I am going to perform right rotation means in this point I am dragging everything towards the left side from the right subtree. So here what will happen? C will be the root node and A will be the left along with its child and we will come to this point with its right child. Okay, and now what will be the position for CL? So the CL is the left child of C, so it must come towards the left subtree only. So the immediate left position is not vacant, so I am assigning this CL as the child of A. Still CL is the child of C only. Now calculate the balance factor. This is 0, this is 0, this is 0. Here as there is no left subtree means this is 0 minus 1, this is minus 1 and here 1 minus 1 is equal to 0 and now this is 2 minus here also 2, 2 minus 1 is 0. We have achieved the perfect balancedness in this AVL tree. So I am going to explain this type of rotation using one simple example. So now consider the tree with the values 20, 10, 40, 30 and here I am inserting 60. Okay, now the balance factor for this is all these three nodes are leaf nodes, so it is 0 and for this is 1 minus 1, it is 0 and here it is 1 minus 1, 2, this is minus 1. So here, now I am going to insert one node called 35. Okay, so 35 means this 35 comes this 35 is greater than 20, so it must come to the right hand side. So in this right subtree 40 means while comparing 35 with 40, 35 is less than 40, so it must come in this left hand side and now comparing with 30 and 35, 35 is greater than 30, so it must present at this point. Now calculate the balance factor for all these nodes. Now this is 0 and here there is no left subtree, so this is 0 minus 1, that is minus 1 and here 1, 2, the level height of this left subtree is 2, so 2 minus 1 is here 1 and here this is 1 minus 1, 2, 3, this is the height. The level of the right subtree is 3, so the height is also 3, so 1 minus 3 is equal to minus 2. In this point we have encountered the imbalance. So what type of imbalance we have encountered? While inserting this 35 to the left child of right subtree. So we need to do the RL rotation. So for this, I am going to do the left rotation in the first step. Okay. So in this left rotation, we are going to take these three nodes into account. Okay, so now for this left rotation, keeping this point as the pivot point and dragging everything towards the right hand side, what will happen? 20 remaining, that means here this 20 and 10, we cannot disturb this 20 and 10 as it remains same. So 20 and 10 will come to this point, and this 30 will go to this point with 40 and 60 as its right subtree, and this 35 will come with this 30, but this 35 is the right subtree of 30. We cannot put immediately here, but I can put this 35 here because 35 is lesser than 40. Okay, so in the second step, I need to perform the or rotation, right rotation in the second step, as I have completed the left rotation. So keeping this point as pivot point and dragging everything towards the left hand side means what will happen? 30 will come to this position and 20 will come to this position along with the 10 as its left child, and 40 and 60 are dragged towards 30. Okay, so now 40 and 60 forms the right subtree as a right giving tree. And now what about this 35? So this 35 is consider this 35 is the right subtree or right child of 30. So it must remain in the right subtree only. So that means immediately I cannot place this 35 in this level because we have 40 as its node, right child of this 30. So I can place this 35 towards the left of 40 because 35 is lesser than 40. So I can keep this as the left side, left child of this 40. Still 35 is present in the right hand side or right subtree of 30. So it is okay now. Okay, now calculate the balance factor for all the nodes again. So the 10, 35 and 60 are the leaf nodes. So the balance factor is here 0, 0 and 0. Here there is no right subtree. So this is 1 minus 0, this is 1, and here 1 minus 1 is equal to 0. And now both the height of the left and right subtrees are 2 only. So 2 minus 2 is equal to 0. Okay, so this is how we have achieved the balanced factor in this AVL trees by performing the right and left rotation in a single while inserting a single value into my AVL trees. Okay, so here we have performed two rotations called left and right. Okay, so that's why we are categorizing this RL rotation in the double rotation category. Okay, so here we have considered this node 35. While inserting this 35, where I am going to insert, whether it is in the left side or whether it is in the right side, we need to consider. Okay, so that is called the special cases of this rotations. Okay, hope I have hope you have all understood well in this matter. Thank you all.